Good afternoon, Professor.
Hello, guys. Nice to see you. Let's wait a minute or so. Maybe more people will join. Okay. So last time we discussed second law of thermodynamics, and believe good to maybe refresh a bit, recall some key points from last discussion and make some general outlook. So it is historically happened like this, that second law of thermodynamics was originally introduced in the scope of research going on heat machines. And that's why initially we formulate this law of thermodynamics from like as on an example of heat machines or heat pumps. So we introduced last time these formulations. So first of all, first formulation that it cannot exist a heat engine which works in a cycle with its own, like if it's only one result of its work, direct conversion of whole energy gained by heat to some useful work. So keep in mind we're talking about not just one process, we're talking about a cycle, and we will discuss during this class in details this Carnot cycle. So all these four steps, four processes which are involved in Carnot cycle, we will understand from it why only part of work done can be actually useful, and the other parts will just will be subtracted. And but the main also second formulation which we discussed was that heat cannot, like energy by heat transfer cannot transfer from a cold body to hot body by itself. So we need to produce some additional work from outside on the system in order to make this happen. And the main message of the second law of thermodynamics. So if first law of thermodynamics defines us just, so it formulates a law of conservation of energy in terms of work and heat, and of course internal energy. However, it doesn't specify in which direction this heat energy transfer by heat should happen. And that is where we need to employ second law of thermodynamics. And this second law of thermodynamics answers these questions, in which direction the processes are going to happen. For instance, we know that by throwing a stone from some height will transform potential energy to kinetic energy, then it hits the ground, and then it transforms its kinetic energy, like gain kinetic energy, to internal energy by heating its substance, its material. So this is quite natural process for us. However, we don't consider a reversible process. Don't consider that at some point this gain internal energy, which is nothing else as kinetic energy of vibrations of atoms in the lattice, crystalline lattice of this stone, can somehow be rearranged in one direction, and that will transform internal energy to kinetic energy of this stone, so it starts to fly upwards. So we don't observe such randomly jumping stones in nature, and that is the more like approach to discuss more general description of second law of thermodynamics, which implies that changes in isolated system always tend to increase the level of chaotic level in the system, and increase the disorder. So all thermodynamic processes, they tend to, in isolated system, they either don't change level of disorder or increase level of disorder. And that is fundamental. There is a fundamental parameter which takes this into account, this level of disorder, which is entropy. And we'll see maybe today or next class, we will introduce this concept, which from more general point of view defines which processes are possible and which are not possible in terms of the direction of energy transfer. So all these questions are directly related to second law of thermodynamics, which we discussed in details last time. And last time we introduced the concept of Carnot engine, which is the most efficient engine possible, like heat engine possible. And today it's time to proceed further with the detailed discussion of each step of Carnot cycle. So let us change the screen. And in order to discuss these steps, we need some pressure volume diagram. So this is volume, pressure. So we consider two isotherms, something like this and something like this. So for our consideration, we will assume that Carnot heat engine is based on a working substance, ideal gas, and its construction will be something like cylinder with a movable piston, so it can move without any friction upwards and downwards. So here we have ideal gas. We assume also that walls of the cylinder, the piston, they are thermally unconductive. So they don't let any energy to be transferred through these walls by thermal conductivity. That's why we can assume that they are thermally ideal isolators. And only this base of the cylinder, it can allow some energy to be transferred through it. Okay, we have a question, and this is question about final exam format. So final exam format, it will be very similar to midterms. Just the only one difference that you will get more problems. I'm not sure still how many. We are still working on this. But obviously you will get more time proportionally to the increase of problems. Then some time will be specified time frame within which you can log in and start doing your final, like solving problems for final exam. And based on your answers in one kappa, you will get your grade for the final exam. So the format is very similar to that one which you are already accustomed with the previous 3 midterms. Okay, let us continue. So only this base part of the cylinder can allow some heat transfer, energy transfer by heat. So this is our model system. So we consider 2 isotherms, and they correspond to 2 temperatures. It's like working temperatures of the hot and cold body. Yeah, you don't need, guys, to record yourself, and also you will get results from long kappa as usually you get it for midterms. So I don't know exactly how long time it takes, but I believe it happens immediately. So it's other thing if in some cases you have some concerns about the problem, you after many checks you believe that you're convinced that this problem is not correct and you gave the correct answer, then of course you can contact me and we will take this into consideration. But other from that will be all the same as midterms. So we have 2 working temperatures, and one is high temperature body, TH, and another cold body, which is T with temperature TC. So now we start with these processes. So first of all, we have some starting point, which is A, and we have isothermal process. So first process is T is equal to TH, and it's equal to it's constant, so it doesn't change during the process. So during this process, we change our state from point A to point B in this direction. So we see that during this isothermal process, we increase voltage. So delta V is larger than 0. So gas is expanding, and it produces some work. So why it happens? Because we gain some energy via heat from this high temperature body. So we get some Q H, some heat. So in this case, piston is moving upwards, and work is done by the gas, so by the engine on external environment. And this work can be defined as the area under this path from A to B along the isothermal curve. So now we go to the second step. And second step, so we get some positive work done by system on environment. So keep this in mind. Then we do some manipulations with our system, and we place a thermally unconductive plate under this base of the cylinder. In this case, since walls and piston are also thermally unconductive, this ideal gas which we consider inside the cylinder will be fully isolated thermally, and exchange of energy by heat will be zero. So there is no heat, it's zero. No heat, energy exchange by heat. And what it means, how do we call this process where we don't have any exchange of energy by heat?
Adiabatic.
Adiabatic process, right? So we have this adiabatic process, which we discussed previously, is kind of steeper than isothermal process on this PV diagram, and it goes from point B to point C. So during this process, we also have some expansion because volume still increases. So delta V is positive. So we can write here that work is, for first process is larger than zero. Work for second step of this cycle is also larger than zero. So we still produce some work. I mean, not we, but the working substance and the Carnot engine produces some work on external environment. However, this is the last step when we actually produce work, because then we need to come back to initial condition, which is point corresponding, like state corresponding to point A. So in order to do that, we employ another combination of two processes, which is isothermal process and adiabatic process. So then we have isothermal process at, also important moment, you see that because of this adiabatic process, since it does some work and there is no gain of heat, temperature in like internal energy and thus temperature of the ideal gas drops, and that's why we go from one isothermal curve to another isothermal curve, which corresponds to the temperature of the cold body. So here we have temperature at the first process, temperature equal to TH, and for the second process is temperature TC. So now the third process is isothermal, T is equal to TC and it's constant. So this is the direction. We go from point C to point D. And in this case, we have conditions when our system expels some energy by heat to this cold body. So in this case, during the process 3, we remove this thermally unconductive plate and put this thermally conductive base of the cylinder on our cold body. So it gets in thermal contact with cold body, and that's why we lose some energy by heat transfer, which is equal to QC. So in this case, we also see the reduction of the volume. So delta V is smaller than 0, and work is negative, means that environment now does some work to reduce volume of ideal gas as the working substance of our Carnot engine. And that means that we already need to, from total work done by the system, which is area under processes A, B, and BC, we need already to subtract area under process CD to get some net, calculate some net work done by the engine. However, it's not the final step. We have one more, which is also adiabatic process. So U is equal to 0. We go from T cold to T hot. And that happens also because of further compressing of the system. We get negative change in volume and some negative work done by the environment on the system. So it will be something like this. So now we close the cycle, and you can see that if we now calculate the area, the work done during the cycle, it will be area under curves A, B, B, C minus area between curves C, D, D, A. And this is nothing else as the area enclosed by the processes, like 4 processes which form the Carnot cycle. So only this part of work can be expelled by the Carnot engine, and taking into account that Carnot engine is working on it's some idealistic model. It's working on reversible processes. Then we don't have any dissipation of energy because of friction or any other losses. And that's why the efficiency of such engine is the maximum efficiency which can be achieved by heat engine. So yeah, here during process DA, the fourth process, we again place this thermally unconductive plate. I just forgot to mention about this, and thermally isolate the system. That's why we don't have any energy transfer by heat. So this is the Carnot cycle. And now, based on this Carnot cycle, we want to calculate its efficiency. So from a previous definition of heat engine efficiency, we have some E. It's equal to unity minus Q C, heat expelled to the cold body, divided by energy transferred from the hot body via heat to the system. So we know this equation, and taking into account known information about specific processes which form the Carnot cycle, we can proceed further with the calculation of its performance. So let's consider first this isothermal process AB, the first step. In this case, QH can be defined as change in internal energy minus work done by A during this process AB. So this is nothing else as well known to us first law of thermodynamics. Then we can write that there is no change in internal energy because this is isothermal process, so temperature is constant, and thus the internal energy doesn't change. So we have 0 minus work done during the process AB. So we know from previous discussions that work done during the isothermal process can be defined by equation nu, which is number of moles, times R times T. So we have a universal gas constant, temperature times natural logarithm of the ratio V initial divided by V final. So initial volume divided by final volume. So based on this, we can write here that taking into account this minus, we can flip the ratio under natural logarithm, and we will get nu times R times T, which is TH here, temperature of the hot body, times natural logarithm of VB divided by VA. So volume in the point B divided by volume in the point A. So let's keep this in mind. Then we consider second isothermal process, which is CD. So during this process, the system expels energy by heat QC. So in this case, QC is equal also change in internal energy minus work done by the process CD, by the system during the process CD. And here we have 0 minus this work. Keep in mind that this work is negative because the system experienced reduction in volume. And in this case, we can write that it's equal to nu times R times TC, natural logarithm of VC divided by VD. Okay, so this is done. Let's go to the next slide. And we can now take a ratio. So we remember, if we come back to the previous slide, we remember that efficiency is equal to unity minus ratio of QC and QH. So we have expressions for QC and QH. Now we can take the ratio. So QC divided by QH will be equal to TC divided by TH. So we cancel out nu times R because it's the same in both cases. Then we have natural logarithm of VC divided by VD and VB divided by VA. Okay. So now we come to the point when we need to deal with the volumes of this gas. So far we know nothing about volumes. We don't specify it. And we need to somehow overcome this drawback. So that can be done by using equations which we also considered in our discussions for adiabatic processes. So since we have two adiabatic processes which connect both isothermal processes, we can write for processes. So we'll come back to the figure. So we have adiabatic process BC and DA. Okay, so for these adiabatic processes, BC, we can write that the product of TH and VB in the power of gamma minus 1, which is this adiabatic coefficient, is equal to the product of TC times VC in the power gamma minus 1. So that comes from the statement which we mentioned previously, that for the adiabatic process, the product of temperature and a volume in the power gamma minus unity will be equal to constant. So this we can write for first adiabatic process. Then we can write for the second adiabatic process, which is the last process from point D to point A. So from D to A, we can write that TH times V A gamma minus 1 in the power of gamma minus 1 equals to T C times VD in the power gamma minus 1. So now we still don't know our volumes, but we actually don't need to know them because we can take the ratio between these two equations for BC and DA. And that ratio will, so if we divide, for instance, second equation by first equation, we will get the following. It will be VA divided by VB in the power gamma minus 1. So we cancel out TH. Will be equal, oh, sorry, it's not. Yeah, I guess it's better to divide first by second, because then we will have the same ratio as in our logarithms. So it will be more convenient. Okay, let's change this. So we divide first by second. So it will be VB divided by VA equals to VC divided by VD in the power gamma minus 1. So from this statement, we can cancel out these powers because they are equal to each other, and then just write that VB divided by VA is equal to VC divided by VD. So now we see that arguments of natural logarithm in this first equation here, natural logarithm VC divided by VD divided by natural logarithm VB divided by VA. Since arguments are equal, means that natural logarithms of these arguments are also equal. And that's why we can write that QC divided by QH is equal just to TC divided by TH. So these natural logarithms cancel each out, and that's why we don't deal with some specific values for volumes at different stages of this cycle. Since this equation is true, we can write that efficiency of Carnot cycle, so this is true only for Carnot cycle, is equal to unity minus, so we substitute TC divided by, QC divided by QH with respective temperature ratio, will be unity minus TC divided by TH. So that is very important equation which we derived. And first of all, it tells us that and the most important message from this, in conclusion from this equation, that efficiency of Carnot engine and Carnot cycle is determined only by temperatures of cold and hot bodies which are involved in this process, and is totally independent on the working substance which is used in Carnot engine. So Carnot engine can be of different design and can use different working substances. However, its efficiency will be defined only by temperature of cold and hot reservoirs which are involved in this cycle. So this is efficiency equation for the efficiency of Carnot cycle. And from other side, we can see that theoretically, it's possible to reach efficiency of Carnot cycle equal to unity when Tc is equal to 0. But it's impossible to reach 0 Kelvin. And that's why normal conditions for operating of heat engines, it's when we have like environmental temperature as cold environment, then Tc is like about 300 Kelvin. So in order to increase efficiency, the only feasible way is to increase temperature of the hot body, so increase temperature of like burning fuel and stuff like that. So this is the approach to go for higher efficiencies with heat engines. Sometimes this equation is used for systems which are quite far away from heat engines in direct relationship. For instance, sometimes this equation is used to estimate some maximum efficiency of solar cells, the converters of solar spectrum to electricity. And how does it work? We can consider, let's say, efficiency, some maximum efficiency of solar cells would be equal to unity minus, so what is called body or reservoir in this system. It's just air environment. So this is something like 300 Kelvin, and the hot body. What do you have an idea what is considered as temperature of hot body? Which hot body is considered when we apply this to solar cell? Any ideas?
Maybe temperature of sun. Yes.
Yeah. So specifically, you need to specify the temperature of the sun's surface. So since we don't really care what is going on for this purpose in the nuclear of the sun, their temperatures are insanely high, but we do care about temperature of the surface of the sun, because that's that part which we can see, and this surface, since it has very high temperature, it's irradiate some electromagnetic waves as quite close to a black body radiation spectrum for this temperature. So temperature of the surface of the sun is about 6,000 Kelvin. So you can calculate and see what efficiency could be estimated of solar cells by considering such Carnot cycle as some ideal model. So would be 1 divided by 300 by 6,000. Will be something like 0.95. So which comes to 95%, insanely high. And this is because we have such a big difference between cold body and hot body temperature. So hot body temperature is very high. It's beyond everything what we can consider under normal conditions, because even tungsten, which is the material with highest melting temperature, its melting temperature is under normal conditions, it's something about 3000 degrees Celsius, actually even less a bit. So we definitely cannot build some cylinder which will withstand such high temperature. But just to underline how efficient Carnot cycle is, that for this particular temperature combination, 95% efficiency, so 95% of heat which is received by solar cell according to this idealistic Carnot cycle should be transferred to some useful work, which is in this case electrical current. However, unfortunately, it's not so realistic, because even calculating ideal conditions, when it's so-called Shockley-Queisser limit, when we have detailed balance between absorption and thermal irradiation between the body, environment, and the sun, maximum efficiency of a solar cell with optimal band gap, it's parameter of semiconductor used to make this solar cell. So the maximum efficiency of the solar cell based on detailed balance theory of Queisser-Shockley limit is 32%. And so far in real solar cells, we couldn't reach this level for a single junction. So this is calculated for a single junction, not multi-junction systems. For single junction, it's something like 24% efficiency is the world record for best examples of solar cells. 24, 25 maybe for very small experimental devices. But we are still quite lower to Queisser-Shockley limit. And this efficiency predicted by the Carnot cycle really gives insanely high efficiency. So you need to understand that this is indeed the highest performance cycle which you can consider idealistically. Okay, guys, thank you very much for attention. We are done with Carnot engine and Carnot cycle. Now we will transfer to the concept of entropy, and that will be during our next discussion on Friday. And that will be our last class for this semester. So I believe everything will go smooth and you will be well prepared for the final exam. By the way, when is the final exam? Who keeps tracking?
It's either in Saturday or Sunday, I guess.
So it's this Saturday.
Yeah, this week's
coming one. Okay, good. Then good luck with preparation and take care. Have a good evening, guys.
Excuse me, Professor, can I ask one quick question?
Yes, sure.
When we calculated the efficiency by replacing the heat by work done in each isothermal process, there was derivation of heat QC by 0 minus WCD.
Mm-hmm.
And is there a typo because there is like 0 minus instead of plus?
Wait 1 second.
Because work was done by on the system.
Yeah, 1 second. So this is here. So we assume we come from the first law of thermodynamics, the like change in internal energy, Q plus work. So Q is equal to change in internal energy minus work. And this minus we take into account because, so here we have minus, then this is negative. So minus and minus gives plus. And that's why we flipped over the ratio in natural logarithm. So it should be initial to final volume. And here we have, sorry, we didn't flip.
Because minus.
Okay, yeah. So we flipped it here because here is minus and this W is positive. So that's why we have this minus, we had to flip. So instead of having VA divided by VB, we have VB divided by VA. And here we didn't flip because we have a minus and this W is negative. So minus and minus gives plus. That's why we have initial volume VC divided by final volume VD.
Okay, got it. And can you clarify, like the first law of thermodynamics? There's some questions. So when there is isothermal process, we always have zero internal energy change. And
Yes.
If work was done by the system, there is a positive work. And if work is done on the system, then there is a minus, like negative work. So that's right.
Yeah, that's
okay,
right.
Thank you.
Yeah, if system gains some energy by heat, so this heat is positive. If then system gains some expel some heat energy by heat, so this heat is negative from the point of view, from the respect of the system, and the same also for work.
Okay, thank you very much.
Yeah, you're welcome. Thank you for questions. Okay, guys, thank you for your attention and see you on Friday. Have a good evening. Bye-bye.
Goodbye, you too.